Welcome back, Eigen family. Welcome, guys. Make sure you like, share, comment, subscribe as always. Check us out on Eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok. And then patrons, thank you guys. Thank you guys as always. We greatly appreciate all your help, the support. The channel is growing slowly but surely. Me and Juan definitely appreciate all we can get. And if you guys want to join the Patreon, it's patreon.com/Eigenbros. Me and Juan do a 30-minute audio podcast there at least every week. So make sure you check that out if you're interested. And then we have the Discord channel to go along with that. And yeah.
Yeah, that's pretty much it. We're gonna run it back for you folks a little bit, and we're gonna do a life of actually, I don't know what the title's gonna be, but this is.
But you can make it whatever.
The life of a physicist, the life of an experimental physicist.
Yeah. So we did this podcast once before. We were trying to see if we had actually done it already.
Yeah.
Because we did, but I think our audio got screwed up last time, so we're going to do the real version of this now.
Yes.
Unless the audio gets screwed up again.
Nah, let's hope not. No, I'm making sure the levels are good.
Yeah.
And they are. I think this is as normalized as it can be. And
sweet.
And we're good. I think so.
Yeah.
So let's get to it, man. I mean, so I guess what can the audience expect from this conversation?
So I wanted to do this one because I kind of was thinking like, okay, what's something we could do that's like not super heavy preparation, and we can talk about that. It's interesting that maybe a lot of people wouldn't know about because, when I was coming into physics, even before I was even in physics, I never even knew what an experimental physicist was. I had no idea there was even a distinction between experimental and theoretical. Like, as soon as I started learning physics, quote unquote learning about, when I've heard of physics with Michio Kaku and, Neil deGrasse Tyson, I thought all physicists were just theory guys who just wrote on paper and then would somehow conceive of the universe through equations somehow, or conceive of the laws of the universe. So then I never even knew what an experimental physicist was. So I figured, this is an opportunity for me and Juan to kind of give a day in the life of what we actually do as experimental physicists. So,
well, 90% of your time is spent crying. No, I'm just kidding. No,
that's every physicist, though.
I don't understand. No, it's 90% of the time being confused.
Yeah, true.
Why doesn't this work? This is not working. 10% is working. It's like, great, I'm a physicist. It feels good. No, but in all seriousness, yeah, I was in the same boat as you, man. I didn't know. I didn't know there was this distinction, and really, when you get into it, you really have to assess yourself, right, and be like, what do I want to do, and where can I play to my strengths in some ways, right?
Yeah, for sure. And there's a lot of different things you can do. And the thing is, what people may not even realize is the majority of physicists are going to be experimentalists. There's little room to have everyone be a theorist, because theorists, let's be real, guys, money is what everything is at the end of the day. So the thing is, theorists, of course, they don't cost money, but instructors don't typically take that many theorists when you're in graduate school.
Because theory doesn't make you money, man.
Yeah, when you've researched, research institutions, they want to be getting those government stipends and whatnot, and, if you're just sitting there with a pencil and paper talking about, how
imaginary particles.
Yeah, exactly. Yeah. And like trying to unify the universal laws, no one really, Jeb and Senator Jeb is not going to give a fuck about what that is unless it's actually going to help with, making missiles or something.
Are you colliding particles? Are you? Yeah. What are you doing? Some LHC stuff? What do you got doing there? It's like I'm thinking Jeb Bush, by the way.
Yeah. That's who I was thinking of as well when I was using that name.
Yeah. Politicians, a lot of it is funding, and Terence is right. As a physicist, you're going to probably you're going to choose either your degree is going to choose for you, or your program is going to choose for you, or you're going to do yourself, because a lot of schools, their theory track is very competitive, like Terence is saying,
Like, I like theory, but I knew there was no ghost and fucking chance in hell that I would ever be a theorist.
Same. I'm gonna be honest. Same.
So I was like, I'm just gonna give this dream up right from the beginning.
I'm too far gone.
Yeah.
I don't know enough. Yeah, I was in the same boat, man. I was just like, ooh, I'm not as prepared as everybody, as like the high theory people coming. Like, you'll realize that you're competing with, like, when you're going into theory, you're competing with cream of the crop. Some people that were trained in their in preteens,
right?
You know, tweens.
It's like when you see, you know, Khabib. What's his name? Nurmagomedov or something. The MMA fighter. When you see videos of him when he's like an 8-year-old kid wrestling a bear.
Yes.
And then he's the guy that's like the main MMA guy now. It's like,
of course.
How do you compete with that? When the guy's been wrestling bears since he's been 8 years old. This is like the physics. That's the MMA equivalent of like the theorists and physicists sometimes.
Like Ed Whitten,
Right.
Yeah.
Where their parents raised them, you know, with integrals.
Yeah. The equivalent of like, it's like in Shang-Chi. I don't know. There's like the new movie where
I have not actually. Put a spoiler.
Well, this ain't a spoiler. This is in
okay.
the movie. It's like a kid being trained to be like basically a really good fighter.
Right.
But this is kind of like the MMA analogy. It's like the kid punching a wooden block till their knuckles bleed.
Right.
And it's like, oh man, I have a long way to catch up. This kid was doing integrals for breakfast, and I was like watching, I don't know, Beast Wars or something on TV, Animorphs or whatever the hell.
Right.
Like, it's just some ridiculous time-wasting activities. But anyway, if you've come on this path, you're probably going to be an experimental physicist. But that's not to shit on experimental physicists, because experimental physicists need to know theory just as good as the theoreticians. But
I wouldn't say just as good, but definitely you're going to go through a fuckload of theory. I mean, you're going to go the full gamut pretty much.
Yeah.
With maybe plus or minus a couple classes that the theorists would take. And the thing is, I guess theorists also tend to diverge into like programming and simulations and stuff. So, I mean, you're going to be matched up in some sense to their level of theory pretty much.
Like, you will at least be able to hold a conversation with a theorist.
Yeah.
They're
like
just
the
more
general
specialized.
knowledge is going to be equivalent pretty much.
Right. And the specialization is literally you're good at collecting data and thinking of experiments. At the end of the day, you have to know the theory, because that way you can come up with really good experiments to validate theory or test theories and stuff like that.
Right.
So you need to know the theory just as good. However, it's not one-to-one with theory people, because theory people don't have to...
Yeah. A theorist... You'll know who's a theorist when you just see them teach undergraduate research lab for one day.
Yeah.
When they don't know how to make a straight line with a ruler.
You joke, you jest, but that's literally like, I had a professor who was just like, he was a professor. He did the 10-minute, 15-minute lecture for the intro lab.
Right.
And then he would have the TA like actually do the setup. An experimental physicist like, okay, this is how you collect the data. The guy was like, I worked at the LHC doing calculations. I don't know any of this. And it's just like, damn. Okay.
Yeah, the experimental physicists are definitely much better at research physics, undergraduate research lab. Because, I mean, it's basically experimental physics, you know, a rudimentary version. So, but yeah, I guess let's actually talk about actually what we do. So, what would it be like? What would your day begin like as an experimental physicist for you?
Well, you wake up, you put your pants on.
So most times.
Most times. No, you it kind of let me create 2 scenarios or 3 scenarios. Academia, lab setting, and then industry setting. And what I mean by lab setting is like you work in maybe national labs, because there are national labs, there are industry labs, and then academic labs.
Yeah.
So for the academic lab, you can expect things to be more relaxed than I think in the other 2 scenarios. because
Yeah.
in academia, and I say this not to shit on academic students or research students or anything, but the pace is mostly dictated by you because this is your PhD program, and like
Mm-hmm.
you will finish as fast as you get your work done, pretty
Yeah.
much. Um, so your day is kind of dictated by you, and maybe your advisor, depends on how they are personally. But
Mm-hmm.
when I was in grad school, that's kind of what I looked at comparatively. I know that um, some labs, I mean, compared to I would say national lab settings or more industry lab settings, it was less competitive.
Mm-hmm.
And yeah, in like national lab settings or industry lab settings, there's much more higher standard, because in national labs and industry labs, like Bell Labs or whatever,
Mm-hmm.
you are competing with other research scientists.
Yeah.
Yeah.
Like their whole mission is to be doing research.
Mm-hmm.
So that's the entire focus in national, research labs and industry labs, right?
Yeah.
And industry labs are trying to release a product a lot of times, right? So they have these deadlines and quarterlies to meet. So they're like, we got to make sure we have X, Y, and Z done before we can even proceed on.
Yeah.
So you have to do this by this deadline.
Yeah, and in the national labs, you're competing with other big labs,
Yeah.
putting out better work or whatever. It's
And sometimes funding's on the line there. Like,
Yeah,
it's
yeah.
like, if you guys don't get
Grants.
this stuff done, then you ain't getting funding for the next round, So it's like, and then somebody else is going to get your money. So
yeah.
the stakes are a little bit higher in those labs.
Yeah. And so why would you say academic is so expanding on that? What would you say makes the academic ground so different in that way?
Well, I think it's because, like you said, it's like the academic at least has the fallback that, students are just trying to get their PhDs with this,
Mm-hmm.
right?
Mm-hmm.
So it's more of like, this is a learning institution. So it's not, the pressure isn't on to produce things for money, although there is some of that for sure. But it's like they can kind of take the hit a little bit because the school you can kind of fall back as this is for learning, not for actually producing some kind of product or some kind of tangible result for you to actually get
Mm-hmm.
money for.
Yeah. So I mean, well, I guess with that, I can say like I can speak on the more industry labs and maybe national lab settings, like, and I think you've had experience in both, so maybe you can introduce the academic sort of lab.
Industry lab, I wouldn't
Industry-
say no.
No, but what
No.
about? But you can speak on like national/academic lab.
Yeah, for sure.
Yeah. So for me, I can only speak on one of those experiences, like industry national kind of experience, and like it's competitive, and when you wake up in the day, it's, how do I say this? You come in a lot of the time with the defined project, and you are working to publish a lot of the time.
Mm-hmm.
So so typically your project, hopefully if everything goes well, is complete in a year. And I mean like collecting data and sometimes writing even, a year and a half. And so you need to be working almost all the time, every day of the week, coming in, collecting data. And data collection looks like, I would say, anywhere like 60% of your time, 70. And in terms of like project completion, and then the rest is writing.
Yeah,
probably.
Yeah.
But the data collection is so crucial. Like
But it's everything, right?
it's everything, because if you don't collect good data, then you don't have paper.
Yeah.
So yeah, in some sense, like you wake up and you work on your projects, but a lot of that looks like, if you want to go into more finer detail, like for instance for me, I would go into the lab picking a couple tasks that I was going to complete that day. And like if you're in a national lab setting, you probably have access to a lot of instrumentation. I know for academic lab settings, it's a lot tighter knit, and it shares
Yeah.
resources with the school. So
Right, because they can't be shelling out money for everybody to have their own AFM or something.
yeah.
Atomic
Yeah.
force microscope.
Yeah. Or like SEMs and stuff, like scanning electron microscopes. Actually, I do have academic lab experience.
Yeah.
Now that I think about it, but anyway, yeah. What was the difference mainly was the fact that I had in a national lab setting, I had a bigger access to more. I had more access to instrumentation and typically
Some really high tech equipment
some really high tech equipment, and
that you could find nowhere else.
yeah, and my projects were more involved.
Mm-hmm.
I definitely knew a lot more techniques going into that, and as opposed to an academic setting, it was a lot more niche. Like I knew how to do one thing really well.
Yeah.
So
And like you said, the equipment access wasn't that always that good because you had to share with people. If something broke, some other grad student was fixing it, so it'd work all fucked up next time. And,
yeah.
You know, but unlike with the national lab, you can like hire an engineer. They'll come out and actually fix it properly or something. It's like just the money access and just the way it's ran is a little bit more tighter in the national facility. But then, of course, it means it's also more annoying too, because then you have to like ask for access and apply for access to things, and you have badges and things to come in and out. You can't just walk in whenever you want.
Yeah, and I'm speaking purely like speaking almost purely from an American perspective, right? Because if I think about all the national labs, and they're mostly tied to universities. Like I'm gonna go from the Pacific Northwest all the way to the east.
Mm-hmm.
You have the PNNL, Pacific Northwest National Lab, in Oregon and Washington, I think. And then there's also California has a bunch of labs. You have Berkeley, you have Lawrence National Lab, you have, God, I know that there's one more. Lawrence Livermore,
maybe Jet Propulsion Lab is
JPL, Lawrence Livermore. Sheesh, that's like 5.
And then there's also like observatories too.
Yeah.
There's like Mount Wilson Observatories in LA, I think.
Yeah.
And which is not really a lab, but I guess it kind of is because it has like an interferometer there and stuff.
Yeah. Yeah, that's true. I didn't think about observatories.
Yeah.
Accelerators too that they have. So yeah. Anyway, they have. I think they have 6 in California, including with Sandia. But then on top of the observatories that you're saying.
Yeah.
And then there's moving further west. You have again Sandia in like New Mexico, and then Los Alamos in New Mexico. And then you have in Colorado, I think you have NIST.
Yep. Which is huge.
Huge.
That's our instrumentation and all of our metrics for things, standards for kilograms and whatnot. So huge.
And then I'm thinking middle of the country, like Chicago, Illinois, you have Argonne? Fermi
Argonne?
Lab and Argonne.
I think. I'm not sure about Fermi. I forget exactly.
No, I think you're right about Fermi Labs.
Okay.
Fermi Labs, Argonne National Labs, and in Tennessee you have
Oak Ridge.
Yeah. Sheesh.
Yeah, we got a lot. Brookhaven has Long Island.
Yeah, Long Island. And then you have National High Magnetic Field Lab.
Yep,
Florida. And because that's in UF too, and FSU. And then you have, what else? Oh, in Maryland you have also you have NIST. And then you have a Jefferson Lab.
NIST?
Yeah, they have NIST office there too.
Oh, okay.
And then they have the Jefferson Lab.
Where's that at? In D.C. or something?
Vermont, Virginia.
Virginia? Jefferson sounds like Virginia.
Yeah, it's probably Virginia. Yeah, the U.S. has a couple small accelerators, right?
Yeah, there's...
Yeah, Jefferson Fermilab and... God, I know there's one more, man.
Yeah, I don't know.
I'm fucking it up. But also Colorado has more national labs. They have the National... It's NREL, National Renewable Energy Laboratory, where they work on literally just renewable energy. And then you have the National Technology Lab or something. It's like just literally just the DOD or Department of Energy or DOE, Department of Energy, just paying money to develop new technologies. They hire a bunch of physicists and scientists and stuff, but I'm thinking all about in the context of physics or something.
Yeah.
And that doesn't even include the amount of observatories that there are in the damn states.
Right.
Right. So
and then, of course, there's all these offshoot things that you probably can't think of right now as well that I'm struggling to think
like
of.
industry labs, I can only think of like Bell Labs. Oh, by the way, in New Jersey, the New Jersey, what is that? The Advanced Institute of Studies.
I'm not sure.
Where all like the bigwigs work, all the big intellectuals. Public
Oh, is
physics.
that where they're at?
The Princeton Institute of Advanced Studies.
Oh, yeah. We see all the YouTube videos.
Yeah. Those people. Oh, and then MIT has their own lab. What is it called?
Not sure.
MIT's. Damn, man.
It's an experimental lab?
Yeah. It's a big lab. Georgia Tech also has a lab.
Yeah, they have the nanotechnology lab there.
They have. But anyway, like, whole point is that a lot of these institutions have their own like kind of like hybrid labs. Like they're some of them are national and some of them are just academic / like public facing labs where industries will come in, give samples to the university or even like the national labs, and they test materials and stuff. Anyway.
That might be not something that's so obvious that people may not know either. Like, because another thing is, like, I never knew that people just didn't do everything in house. Like, sometimes, when we'll do an experiment, like me and Juan will do an experiment, you'll get samples from somewhere else. Like, some group will specialize in making a particular kind of material. So, like, literally, you'll think of like a wafer. Like, you might see the silicon dies that they cut, with these machines. These precision machines to make chips and whatnot. You might have like a special die of some kind of material where you'll do a measurement on that to test the resistance of that material under low temperatures or something. So you'll get that material sent to you from some other national lab. Then you'll do the experiment in, like, let's say some kind of cryostat, which is just something that gets to really cold temperatures. And then you'll do just what they call IV curves on them, where you'll get the current versus the voltage, so you can find the resistance. So that would be an example of like what a typical experiment would be in condensed matter, let's say.
Yeah. Another thing in condensed matter you would see would be like measuring, essentially condensed matter just measure the behavior of electrons, like in your system, both and the two dimensions that it splits into is the electric. They call it transport properties, and you're going to hear this a lot. But it encapsulates like what the carriers or whatever the electrons are doing in both magnetic environments and electric environments. So you'll have typically like some kind of like quantum design is a big player in the game in data collection. They make instrumentation like with magnetic responses called the MPMS, or sometimes it's called the SQUID.
Yeah. I didn't know those were the same.
Yeah. Magnetic Properties Measurement System for the MPMS acronym, and then the SQUID. A SQUID stands for Superconducting Quantum Interference Device.
Oh, okay.
Yeah.
Interference.
Yeah. They're magnetometers used to measure extremely subtle magnetic fields based on superconducting loops containing Josephson junctions. But yeah, that's SQUIDs. They're used interchangeably with MPMSs, or magnetic, what is it called?
Properties.
Yeah.
Something.
Yeah, it's a SQUID. It's basically a SQUID magnetometer.
Okay. Never knew.
So yeah, you'll be using that to characterize the magnetic response of your system, and it's really characterizing the behavior of electrons. And you have this with like in the electric sense, when you're measuring like IV curves, like you're saying, measuring the electronic response and see how your resistivity changes. Because in physics, a lot of properties are tied to resistivity, like carrier mobilities, like how good especially for applications. But resistivity has a huge play. Like if you look at our last video, fractional quantum Hall effect.
Right.
Like that tells you some very interesting stuff about the physics of your system.
Right.
Yeah.
And that's a lot of condensed matter physicists, is a lot of just testing different materials. Like just doing weird stuff to materials, putting it under high pressures, putting it under low pressures, shooting lasers on it, optical properties, magnetic properties. Like basically it's just like characterizing things with all these different metrics you possibly can do on it.
Yeah.
And that's pretty much the majority of condensed matter physics is just like figuring out material properties.
Yeah, material properties in the context of like what the electrons are doing. Like a lot of it is like analyzing like what the Fermi surface of how it looks like. You're mapping the electronic behavior, what the bands look like, the electronic bands look like.
Right. These are like higher level things that just
Yeah.
are better for characterizing like certain
Exactly.
parts of the system. Like you start to get your mathematics and theory involved, and you can
Exactly.
do like what Juan's talking about with band theory. And we have these charts like dispersion relations, what you call them, where you're looking at energy and frequency and things.
Yeah.
Frequency is a really important metric in condensed matter as well.
Yes.
Like, or in experimental physics in general, when you can get frequencies, which is like the counts of things. Let's say you have a cycle of something, like, you know, you can think about atomic clocks.
Mm-hmm.
Like the way atomic clocks count a second is like 9,000 transitions of a cesium atom between states or something.
Mm-hmm.
And the nice thing about that is it's like this discretized thing where you can count the number of transitions.
Yeah.
So it's like, oh, I've hit 9,000 transitions. That's 1 second.
Yeah.
So experimentalists love frequency measurements because they're very easy to, I mean, they're really reliable when it comes to like actually determining quantities.
Yeah.
But anyway, that's kind of an aside.
No, it's true. I mean, look, I think the most important thing to know as an experimental physicist, or the most important thing you learn, is how to collect data. Like,
Pretty important these days.
Yeah.
Especially if you want a transferable skill, because, you know, nowadays it's like all data.
yeah.
If you can analyze and manipulate data, I mean, that's an extremely useful skill.
Yeah, especially if like you are trying to work in different environments as an experimentalist. You need to know how to work current sources, or like, you know, work with different like amplifiers, or you know, that kind, like basically instrumentation that helps you filter out noise in your data.
Yeah.
You know what I'm saying?
Yeah.
Like that's really crucial, and applies universally to a bunch of different other avenues of measurement, because you're collecting data, and like Terence is saying, a lot of experiments, you're just knowing how to manipulate your data.
Yeah. And actually, you bring up another good point there, Juan, is like another thing that kind of separates the experimentalists from the theorists, right, is like real life noise.
Yeah.
Like in real life, things are messy, right? So you're always having to deal with like a bunch of junk that you have to filter out. So you have to know what things you can filter out. And, you know, we typically call like junk noise in experiments, because you'll see like in the background, you'll see all this junk, and you kind of have like this small signal or something, or maybe not a small signal, but you have a signal that you have to try to extract, and you want that nice, neat signal, and then you want to just filter out a lot of the crap. So, you know, this requires you to understand what's actually happening, so you know what to filter out, you know, and you're not filtering out the wrong stuff. So, you know,
true.
Yeah. So if you know how to filter noise and you understand how to do that kind of thing, then that's one of these skills you learn in experimental physics. You become good at dealing with the chaos of normal life, you know.
Yeah. Like, and the filtering noise thing is just so, it saves your butt, because now you start seeing, at least for me, I started seeing like the real applications of the theory in person, because you know, when you're reading about second order like effects, or like these kinds of things that in theory they kind of just brush away, they're like, oh, you know, these are just fringe things. In the lab, you actually start seeing second order effects sometimes, like, yeah, like a lot of things are linear with the first term, you know what I'm saying? Like, oh, so and so equals this, and that's all. That's the nice little equation you see.
Yeah.
But what they don't show sometimes is like the second order or third order terms that can sometimes get bigger or contribute more in different scenarios. You know what I'm saying? Like, and that's something you see in experimental physics, like, because sometimes you're just scratching your head, you're like, why am I seeing this?
Yeah. But it's like, oh, this is real life.
Yeah, this is not
so
an
now
ideal.
now these terms actually mean something. You can't just throw away the rest, right?
Yeah, exactly.
Or at least if you do, you need to know what you're doing.
Exactly.
You know?
Yeah.
So yeah.
In some ways, you do learn theory a lot more in depth than some theorists, because
right, because theorists is just like, oh, second order, I don't give a fuck about anything else. So I'm never gonna even have to care about this extra stuff.
Yeah. Because in your data, you'll sometimes, like, you're supposed to get these nice plots.
Mm-hmm.
If everything works out, you get these nice plots, and it observes theory beautifully.
Mm-hmm.
But like Terence is saying, if you have noise or maybe other contributing effects, maybe your material has something very interesting about it, and you're characterizing a new material or something, and you see something that doesn't fit the theory, you still have to know the theory well to be like, oh, actually, this can be described by, oh, this is a ferromagnet, so this means it actually doesn't necessarily obey this equation.
Right.
There's some other effects that contribute to this.
Right.
Yeah.
You need to understand really what's going on. So that's why you actually do need to know theory. Because if you're just throwing away data willy-nilly, I mean, that's not going to fly in science. You have to actually have explanations for what you're doing.
That honestly almost happened to me.
Oh, really?
In my project. Because we didn't, I was measuring this new material, and my advisor was like, what the hell is this? He was just like, what is this? He thought I fucked up. He was like, this doesn't look, I need you to run the experiment again and to verify it. And I did it again, and he's like, And he's
it was
like,
the same?
Yeah, and then we did more experiments, and then literally like a year later, he's like, God, I still don't trust his data. He's like, can you do it again? And I'm like, sure. I mean, dude, I'm doing the thing. He's like, wow, okay, all right, this is the data. And I'm like, dude, yeah, there's a lot of things.
You have to, it takes convincing yourself when it doesn't align, because you're just like, because I mean, the more likely culprit is always, I'm fucking up.
Yeah,
right.
Yeah,
You're fucking up usually.
Yeah.
Most of the time. So so when it doesn't follow theory, and it's not you fucking up, then you're really like, okay, what's really happening here? Then and that's interesting usually, because then that actually does yield something new a lot of times.
Yeah.
Like then you have to start actually correcting your thoughts about things.
Yeah.
But you got to be sure. You got to make sure it's not you first.
Yeah, and that's going to be a lot of like your experimental work, just being like validating and cross-checking with like what is known and everything that you contribute, because there's things that you learn, there's tricks of the trade essentially. There's stuff with like, it never crossed my mind that our instrumentation is at like 60 hertz.
Oh, right.
And sometimes when like you see where I'm going with this?
Yeah. When your sample rate is off, now you see different things. Is what you're saying?
Yeah.
This is the kind of thing you have to actually care about in real life.
Yeah, exactly.
Like you have to see what your instrument's limitations are and things like that, or what noise levels your instrument has, or what data precision and resolution you have with your instruments. So you have to actually care about all this stuff.
Yeah, and so for those of you that aren't familiar, like when you take data, your sample, like most electronics that we have, their frequency of the current, the AC, right? It's alternating current.
Sure.
The frequency that it has is driven at 60 hertz, I think.
Or multiples, or 120, or multiples of 60.
Of 60, yeah. And so with lab instrumentation, if you're collecting data at any of those multiples, you can sometimes pick up some of the electrical noise, because it's obviously plugged into the same outlet. So you can, some people will sometimes see like, I've had this in my lab, if somebody's new or something, like they'll just like have harmonic effects. And this is like, they're like, wow, this is not supposed to be behaving like this. I'm like, yeah, you're doing, this is a rookie mistake, my friend.
Yeah, we even had an issue where there was some weird shit that would happen because, being in Florida, there would be humidity sometimes, and then you would get this fucked up data because the humidity would get into the instrument, and people were like, what's actually going on here? Because the lab is right next to the outside door, so people would be coming in constantly.
Oh.
And it's just like, and then they had to actually figure out how to get rid of the humidity. Because
That's so funny.
This is the things you have to worry about with experimental physics is like the real life things that you don't really have to care about in theory. You have to make sure everything is taken accounted for.
Yeah, for sure. And it's such a rigorous process. Like you need to verify and validate your data and cross-check and reference it with other works, and
and people from other regions and things to make sure it's not regional mistakes and whatnot.
Yeah, exactly.
Yeah, it's a process.
It's tough work, folks. It's not easy. It's not easy because a lot of the time too, as an experimentalist, sometimes you come into work and you're like, damn, my project, it ain't going nowhere.
Right.
Or you get scooped,
Oh,
or
yeah,
somebody
that sucks.
publishes your work,
Yeah.
and
And
then
then all your stuff was just kind of done in vain in some sense.
yeah. And this is harder to do in theory. It's harder to get scooped in theory.
You think?
I'm
not
I've
sure.
heard.
I think Leibniz or I think Newton's would disagree.
Oh, Newton would Well, like from what I see, like PhD theory students, they take on a project so unique to their own kind of like
Oh, I see what you
specialization
mean. Yeah,
that
PhD. Yeah.
but experimentalists, they compete. You know, you have a family of compounds out there, and a lot of the time, if it's a new material and it's really exciting and everybody's trying to look at the physics of it,
Right.
you're competing.
Graphene.
Thank you, graphene.
Everybody and their mother jumps on graphene anytime anything interesting happens with it.
Yeah, I mean, the most recent one is the twisting bilayer thing.
Yeah.
With graphene.
And then you know that one with everybody jumping on that. So
Now everybody started twisting bilayers and whatnot. So, and that's kind of the thing. You kind of get scooped if you're like, oh God, like let's look at the physics, and then like you're trying to be the first to publish. It's more competitive.
But I guess to shift gears a little bit, I wanted to see not so much, but we should also talk about experimental physics in other areas of physics as well. Like, because there is nuclear, there's
astrophysics, nuclear.
Yeah, there's
particle
astrophysics,
physics.
particle, all that stuff. So what are the differences, I guess, between those, you think? Or what? Let's just try to describe some of those areas, too, for people who might be interested in that.
Well, if you want to see a good reference for this, go look at Andrew Dotson's interview that we did. I'll go ahead and link it at the card, maybe.
Wait, Andrew Dotson, we did with him?
Yeah. He talks about his research.
But he's a
life.
theorist.
Yeah, but he was talking about, I think he does some data collection, no? I thought he did.
I'm not sure. I know he does stuff with the proton.
Yeah.
Yeah, so it's
I thought-
nuclear research.
Yeah, but I think he works no, he is a theorist, but I thought that he worked.
Oh, he does programming, maybe? Because that's
Maybe
another
so.
thing about theorists is they do some real life stuff in some sense because they do like simulations.
Yeah.
Or they'll do like programming or something to look at, they'll run some kind of like, iterative process to look at something. But I think Andrew's theory, so it's a little bit not in the same vein because he's not measuring anything in real life.
Yeah, but maybe I'm confused. But
He uses real data though because he's looking at
Yeah.
the mass of the proton, right?
yeah, I mean experimental stuff is important because in particle physics you're kind of also working as a condensed matter physicist. If you think about it, because
like everybody's kind of a condensed matter physicist at the end of the day, experimentally.
because you're building detectors which detect photons or maybe even electrons, depending on the
Or just particles in general, whatever
or
they
just
may be.
any particles in general.
Yeah.
Yeah,
A lot of the times the particle people are just shooting things down a long track. Right. They're just shooting particles down a long track and then colliding them. And then
Scattering.
seeing what gets produced. It's the LHC, it's the, Brookhaven, it's the Fermi Lab, it's a lot of these places. They're just using linear accelerators, synchrotrons, which is the circular one, and they're just seeing particle explosions all day and then just taking that data. So
yeah.
that's what you'll see a lot of in particle physics.
Yeah, and then these bigger projects, I mean, if you're doing a PhD project, you're building detectors by scratch or from scratch. You're maybe making the film to detect certain particles. Like if maybe the particles you're detecting are within like a certain spectrum of energy in the electromagnetic spectrum, and you need to fine tune that and amplify it. You will sometimes build a film or something that can help detect this range of particles and amplify, and then you can amplify that signal, and then wham bam, that's the whole project, because now you built a whole project just to amplify the signal that you're looking at and collect data, and that's like a huge contribution, obviously.
Right.
And yeah, so we knew a guy like that. Shout out to Jesus. I'm not gonna say yeah. I think he was pretty much doing that. But I mean, like look at the what is that experiment with the graviton or something, where they had like underwater tanks or.
You're talking about the neutrino.
Okay, it was a neutrino.
Yeah, so there's the Ice Cube Observatory, is what they call it actually. even though it's not an observatory. I don't know if what it counts
Is
as
this the one in the
observatory.
Arctic?
Yeah, it's the one in the. You can literally work in Antarctica. There's literally people in Antarctica right now looking for neutrinos, and they actually stay in this like facility. And actually, the guy's on TikTok. One of the guys that works there is on TikTok, and he's got
Nice.
an interesting TikTok. And that's IceCube. And then there's also the Super Kamiokande, which is in Japan, I think, which is another neutrino detector. Uses the same kind of, setup in some sense, where they got these giant fucking detectors under ice. Because I guess ice filters out all the kind of the larger particles like protons and whatnot. And if you get any detections, it's going to be neutrinos, basically. But of course, neutrinos are weakly interacting pretty much with everything in matter. So you only get like one every so often or something. Well, I mean, actually, should I say weakly interacting? I don't know if you can call it that. Maybe that's the
think they
wrong
are.
word. Put a big asterisk by that because there's a weak force.
Yeah.
And I don't know if that's what they're reserving that word for.
We can have our correction robot fact check.
Because weakly interacting particles are related to dark matter. Neutrinos are different.
You're right.
So I don't know if that is the same. If I can use that term, probably not. But anyway, particle physics is pretty straightforward. You may ask, like, why do people collide particles and shit? Like, who gives a fuck? The thing is, like, you can collide particles and produce new particles from them. So sometimes particles we never would see in real life, you can actually make them when you have high enough energies. Like, for example, the Higgs boson. There ain't no Higgs bosons just around and about every day.
Right.
Like, the energy scales that you need to create it have to be on the order of, like, the beginning of the Big Bang or the beginning of the universe. So you can only see that particle when you're colliding things at super high energies.
Yep.
Because it decays so fast, I mean, it just turns into other particles that exist normally in everyday life. And a lot of these things we can't really see. So it's a way to continue formulating the actual model of how the universe is made or what particles the universe is made up of by using these really high energies to collide and produce these particles that just don't exist normally. And that's pretty much particle physics. I guess we can talk a little about astronomy. So astronomy is interesting because, they are kind of more straightforward in some sense where you just are looking at the sky. You could pretty much, most people can conceive of astronomy. Like you're looking at pictures of, the planets, you're looking at pictures of stars. But then there's some other aspects of astronomy you may not think of, like, they're looking at cosmic background, the cosmic microwave background, which is the microwave background that's produced after the Big Bang. And that's a way you can create, simulations and things from that and kind of back engineer how the universe was supposed to look, 13 billion years ago from that microwave background. And yeah, there's a bunch of interesting things you can do with astronomy, like also look at the spectral lines for different planets to see if they might have the ability to sustain life because they have water on them and things like that. So
yeah, and spectral analysis looks at the elemental composition.
So there's interesting things you might not necessarily guess that astronomers do as well.
Yeah.
With their extra instrumentation. And even you can think of the new kind of astronomy that just came about with LIGO and Virgo, because now there's gravity wave detection, so you can actually cross-reference your gravity wave data with the astronomical data and see what actually produced those gravity waves. That's how people were able to determine, like, oh, these gravity waves came from black hole mergers and things, because then the astronomy data can corroborate that data. So, I mean, astronomy is pretty, it's gotten to a new era now in some sense with this gravity wave detection.
Interesting. Me likey.
Yeah.
No, I mean, you look with astrophysics, you have star formation or galaxy formation, you have black hole stuff.
Yeah.
Cosmology, that's kind of like in that same vein. And yeah, a lot of the theorists, like Terence is saying, take in experimental data and then they apply different models to the data to try to explain what they're seeing.
Yeah. So what would you say, Juan? Would you say experimentals came first or the theorist? It's like the chicken or the egg problem.
It's definitely experimental. Like you think about a lot of look at the fractional quantum Hall effect. It's like a lot of it wasn't discovered until experimentalists like kind of just like probing, and then they're like, oh, this is strange. And a lot of it is really just fucking around and finding out. Like it's just like
True. It's true, man. That's
Yeah.
why when I laugh when people talk about the scientific method, as if there's some like formulaic way to do science, it's like really you just fucking around. And then when you fuck around enough, you find some shit that's weird, and you're like, oh,
Yeah.
that's interesting.
Yeah.
I mean, there's no right way to do science, folks. I mean, it's just you just mess around and then shit happens. Of course, as you start to play with more dangerous equipment, you got to actually start thinking about what you're doing.
Right. No,
You can't just be producing, tera electron volt collisions without actually knowing what's happening.
and you get more credit whenever you like actually have a theory or a nice hypothesis before coming in to a experiment. But here's the thing: a lot of the time, good research is taken as you have data and then you have a hypothesis and a model, and if it fits your model or not.
Yeah.
There's some papers where it's just like some people are just reporting data. They're just like, hey, here's the data. We have no clue what it is. We have zero hypothesis.
Right. This weird thing was found. This anomalous thing.
Yeah, exactly.
This anomalous effect was discovered.
And we have no clue what it is.
So it's up to you guys to try to make this make sense.
So in that way, it doesn't really fit the scientific method when those papers come out.
I would say it does because, that's the process of just doing and finding.
Yeah,
That's
doing and
science.
finding is a more simple one, but I'm saying like the one we're taught in school is have a hypothesis.
Oh, right. Right. Test the hypothesis.
Yeah.
No. It's not how it goes all the time. Sometimes your hypothesis is just like, oh, I've got funding for this new equipment, so I'm going to try to just, slam shit together and see what happens. That's kind of what the LHC was. We had a hypothesis for the Higgs, but we found other particles along the way, right?
Yeah.
I think it was like some crazy number, actually, of new discovered particles from the LHC. It's like 50 plus particles or something they've discovered.
Yeah.
And that's not even related to the Higgs. So, I mean, it's just like, yeah, the more crazy equipment you have, and the more. That's one thing also we've been doing. It's like the obvious ways to find new physics in some sense is to crank up the energies and then to scale things down or to make things large. It's like exploring these extremes is kind of where the leading edge stuff is. But now I'm kind of wondering, I'm like, have we like tapped out, the extremes yet? What do you think?
Nah, man, I think, look, I want to get into quantum computing, and that's kind of one of the reasons why it's like, oh, we still don't really know. I mean, we know quantum mechanics. We know how to do quantum mechanics.
Yeah.
But we still don't really understand quantum mechanics. So it's like, it tells me that there's a lot of things that are still have yet to be formulated properly.
Yeah, it feels like we're in the infancy of quantum mechanics too.
Yeah.
Even when we learn it in school, I'm like, because also the sheer low amount or the low volume of problems.
Right.
Because you think about quantum mechanics, there's only like 5 or 6 different potential wells you can really solve.
What? I thought there's probably less.
Well, I'm just thinking maybe the extra
Dirac,
variations and things.
Okay, the Dirac potential.
You can have like double Dirac and all that kind of stuff.
The what potential well, infinite square well,
the scattering.
So
there's
actually, no,
something
you're
like
right.
that.
You're
It's
right.
like a
You're totally
handful.
right because there's like a nice diagram of all the different potential wells.
Yeah. I don't even know if it's 6. It's something like a handful, though.
Yeah.
Right? So, but you think of that, and then you think of, like, the sheer magnitude of problems in electricity magnetism. Like, there's just so many fucking problems, right? And that's the one that's our most complete theory.
Yeah.
So I'm like, you know what? I feel like quantum mechanics has just only begun.
Yeah, it's going to be one of those things where, it shows that we don't even know how to deal with gravity in a quantum sense.
Yeah.
But to me, damn.
I don't even know if that's the right approach.
Yeah, me too. Like, gravity could be an emergent phenomena of something.
I don't think gravity is a particle. I just don't. I think it's space-time only.
I think it's an
my
emergent
hunch.
phenomena. It could easily be like, well, it just falls from. There could be no quantum equivalent of gravity. It's just like this thing that just happens when mass is. It's space-time, the curvature.
Yeah. I think gravity is space-time and nothing more. But then this is also a big asterisk because I don't know shit about
We're not
quantum theory.
We're not field
theory.
theorists.
So I really have no fucking I mean, we're physicists, but I have really no fucking room to talk about this in any kind of qualified way.
We're physicists,
So
but not
just know
field
this.
theorists.
Yeah. Because, I mean, most people who are on the leading edge of this theory of everything stuff would say that you need to quantize gravity to make a theory of everything. And I even heard that they have ways to quantize gravity, but it's just like it doesn't fit fully or something.
Mm-hmm.
But besides all that, I just in my believy, center
In my intuition,
in my heart, I just believe that I think, to me, it seems like gravity is space-time only. But this is a very uneducated opinion, so take it for what it is.
Yeah, my assessment of that is too. It's like, well, I see a lot of things are kind of emergent properties.
Yeah.
Like StatMech is kind of an emergent property of quantum systems becoming entangled, right? And in that way, like the entanglement. The point is that I think it's like the emergent property of it. There's a lot of emergent properties in physics that kind of lend to their own disciplines.
Yeah.
Do you see what I'm saying?
Yeah.
And I think gravity might be one of those where it's like, well, just there's complexity in the system, and it adds to bring this whole subject.
Mm-hmm.
Where I don't know, but maybe you know what? Maybe we should learn field theory, and then we can get back to this.
Well, we've been trying a little bit with the podcast, but it's a lot to learn. Field
It's
theory
hard
is
to teach
deep, and every
yourself
time I
field
look at the
theory.
textbooks, it looks like there's just so much going on. I'm like, damn,
Yeah.
is this one subject?
Yeah.
It's not nice and packaged up neat like E&M or quantum or anything. It's like
Nah.
there's so much shit going on.
Yeah, at least Griffiths makes it easy to teach or easy to learn from.
Oh, and shout out to Dietrich Labs. He actually did a recent video on string theory. He solved the simplest string theory problem.
What is that, a harmonic oscillator?
Probably. I don't know what it is though.
One-dimensional harmonic oscillator?
It was an hour-long video, and I was like,
Oh, nice.
God damn, for one problem.
Nice.
But that's like the ultimate level once you're going to get to string theory level, because that's now superseded even quantum field theory, right?
Mm-hmm.
I really want to watch that video at some point when I can actually understand what the hell's going on.
Yeah.
But yeah,
Well, do you think we covered all the aspects of like the experimental stuff?
I think so.
What would you say is a day in the life of I don't know, like academic, like I think we covered all
Experimentals?
bases. Yeah, I think we covered all bases.
Yeah, I think it's just basically, we come into our lab and come into office, go on the computer or go in the lab, do some measurements, a lot of measurements, taking data, putting it into some kind of data, spreadsheet program. And then you try to interpret that data using the equations and things that are relevant.
Yeah.
Long story short, and then reading a bunch of papers.
Yeah, I mean, a lot of it is, in summary, just to add on, in my experience, like, come in, collect data, talk to your advisor, show them the data, be like, hey, look, this is my data. And either they like it or they don't.
Mm-hmm.
And if they don't like it,
Mostly don't.
Mostly don't. If you don't like it, back to the drawing board, and then you have to collect more data or, like, I don't know. Just a lot of the time, it's just you collecting data, checking in with your advisor, doing lab meetings maybe, reading papers. Sometimes they'll send you papers. Sometimes you just look for yourself, and you just try to sort your thoughts out on the project.
Yeah.
Yeah.
Yeah, I guess to sum it up, I would just call experimentalists engineers who never leave the prototype phase.
Yep.
And they suck at engineering.
And they suck at engineering. That's so true. Yeah,
That's basically what an experimentalist is.
Experimentalists are meant for R&D, and I'm fine with that. My ideal position is doing like research and development.
Right.
Like, preferably more on the research part, because I have no development skills.
I guess I should just say bad engineers. An experimentalist is a bad engineer who never leaves the prototyping phase.
Yeah.
That's my sum up for an experimentalist.
Mm-hmm. And engineers don't ever have them. Engineers think they can do science and research, but they can't.
No.
Like,
They don't have the deep enough knowledge to create like the really new, leading edge stuff.
yeah, I spoke to electrical engineers before, like in my undergrad, and they were just like, yeah, they would ask me about E&M, and they pretended to like know more than I did, and I was just like, bro, I'm a physicist.
You can always tell too. You're just like, okay.
I'm like, all right, dude. All right, okay. And they would just, anyway. But this is why we specialize, folks. You know,
Yeah.
we each bring something to the table,
Right.
a certain level of specialty, and you play to each other's strengths. So,
Right.
so yeah,
Makes the world go round.
it does. But
Anyway.
any lasting questions
From me,
for the
questions for
folks,
the audience?
For the audience.
I guess audience, what do you want to hear? Did you have anything specifically you wanted to know about experimental physics, or maybe what does it entail? You know, just leave a comment, ask us, you know, what it is, and we'll get back to you. I do read the comments, so you know, guys, leave them.
I do too. I skim them, but I don't leave comments. I'm a lurker.
Yeah, I'll leave a comment, and then occasionally I'll show Juan, and he can answer one.
But I'm a lurker at heart, so I don't.
Yeah. I am too, but I've learned to be a non-lurker just from doing Eigenbros.
The branding.
Yeah, exactly. Because you got to engage, you know. Your audience wants to talk, and, you know, it's good to get feedback and have a discussion. So, you know, I've broken that lurker habit now. But the shitty part is it makes me on social media all the time now.
Yeah.
That's the only downside.
But yeah, folks, questions, comments? If you're in undergrad, good luck.
Yeah.
If you want to be a professional.
Hopefully this will help somebody, like, actually know what they're doing, though.
Oh, know what you're getting into, actually.
Yeah. So if you hate doing things with your hands, then you better go hard on that theory track. You better be fucking in the books.
Head in the books. And if you're an experimentalist, my advice is to, and this is one thing that I did not spend a lot of time doing, but I should have in grad school, was really honing in on the techniques for like hands-on stuff, meaning like you're working your current sources, knowing how to do like VI stuff, and this is using LabVIEW, this program. Where
I would highly recommend taking like a hands-on like lab class or something. Yeah. That's going to probably be the most useful skills for you. If you can take engineering courses too, even that are like hands-on based, that'll be really worth your time.
Yeah. LabVIEW is probably one of your best techniques because you can then LabVIEW is used for instrumentation, to set up instrumentation to talk to other instrumentation to help you collect data. So, and we do this, they have this in different across all labs I've seen.
And that's kind of like one of those softwares that will get you on a job immediately out of school, because no one has LabVIEW experience who isn't in STEM, because it's such a proprietary thing that no one else really has use for. It's kind of a stupid software in some sense too. It looks like a mess of spaghetti wires. Like when you look at it, it's like a shitty Visual Basic, but it's powerful. But if you learn LabVIEW, you will get calls from jobs. Like I got many calls with people asking my LabVIEW experience, and I'm just like, I didn't want a job just doing LabVIEW, so I usually just am like bullshitting. But if you want to just get a job straight out doing LabVIEW, that's a good way to get hired, because it's a specialty software, and everyone uses it.
And as an experimentalist, learn that LabVIEW. You know how to use current sources. Look, I did like a crash course summer kind of like a summer school thing to teach me these techniques. So spend time learning how to use the instrumentation for different kinds of experiments. Maybe you're using like a resistance bridge or something. Maybe you're learning how to do low temperature measurements. You need to use certain equipment for that. And you know, you're using preamps or amplifiers and maybe different like frequency generators. You know,
understanding data acquisition, cooling as well. If you can understand like different kinds of cooling, cryogenic cooling, liquid cooling, that's all useful.
Learning how to work with cryogens, laser safety, all that kind of stuff. These are things. I mean, if you're
PPE in general.
Yeah, PPE in general.
If you got all your protective equipment. Don't shine your eyes out with a laser. I mean, nobody needs that.
I mean, really get into it. Like, the tools of the trade are like, at the end of the day, my thing, LabVIEW. Learn how to use raw data collection things like Sanford Research instrumentation or Keithley instrumentations, like current sources, resistance bridges, those kinds of things.
Voltmeters,
function generators, those kinds of things. and some kind of programming language to help you analyze the data. Or you can do it by
probably one programming language is good, or maybe a couple.
Yeah, there's still professors that use like Origin Lab.
Yeah.
A lot of people use Origin
A lot of
Lab.
them use it.
Yeah.
Yeah.
But I don't like using Origin Lab because it's like
Really?
clunky.
What do you like?
I like using Python.
Oh, okay.
Just to make graphs on the fly. Although
I see.
Origin Lab does make you better at making pretty graphs.
Mm-hmm.
You can do it.
I like Origin.
But it's so manual. It's so inefficient in my opinion.
Yeah, I think it's good when you just want something quick though. So I can just throw it in that plot real quick and just see the graph and it's all good.
That's true. But Python for me does that quicker because I'm just like calling on.
But you can do programming in Origin. You just have to know how to do
never
it.
did
Yeah, I never did it either.
Yeah.
But you can if you want to become like a super user.
Like Origin Lab?
Yeah,
Oh,
I'm
I
pretty
didn't
sure it uses like C++ or something too, so
shit.
it's actually useful.
Well, not for me. But anyway, folks, yeah, I think that's it. If you're an experimentalist,
Yeah,
bless your soul.
If you got anything to correct us on, let us know.
Yeah. And I think that's it. Don't forget to like, comment, share, subscribe.
Indeed. Check out Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and then patrons. We appreciate you guys once again. Patreon.com/Eigenbros if you want to join up. Audio podcasts every week, and then there's a Discord channel. $1.
Yeah, $1.
That's all, folks.
Thank you, folks. We'll see you next week.
See you guys.
Peace.